There we go. Okay. So we're recording. It's live. Welcome back. Well, reading week. Work week. It's never long enough. I'm very happy to see you all, but you know, if it had been 2 weeks back to back, you wouldn't have heard too many complaints. I think you probably feel the same way. So, what I want to do today is I got a bunch of good questions that directly relate to the thing, so I think we're going to jump right into those. And if other stuff comes up, that's great. But what you should have watched by this point is naming of RNS, looking at RNS, assigning RNS, and doing that kind of thing. So we're going to do some problems in that space. So this question basically asks, identify all stereocenters with an asterisk, assign RRS to each center, and E and Z to each double bond. Okay, so when we're asked this question, we need to first remember is what is the definition of a stereocenter? It's any carbon attached to 4 different atoms. Being attached to a lone pair doesn't make you a stereocenter, even if it's 4 different things, going back to the thing, because there's one example in the assignment, for example, where I show that the lone pair on nitrogen can flip back and forwards. So it's not stable. So lone pairs move. But when you're attached to 4 different atoms through 4 different single bonds, they can't interchange. Those are stuck. And so that's how you can get a stereocenter, is if you have 4 different things. So if we look walking around the molecule, you can do this as anally as you like. This carbon and this carbon in red, actually all the carbons I'm marking in red, are attached to 2 hydrogens. They have to be. In that case, none of those can be stereocenters because 2 of the things they are attached to are the same. This guy out here, of course, is attached to 3 hydrogens, to a different color, as are these other methyl groups. So again, those cannot be stereocenters. Similarly, the double bond cannot be attached to 4 different atoms because there is a double bond. You need to be sp3 hybridized to be attached to 4 different atoms. If you're in a double bond, you are not sp3 hybridized, so you can't be a stereocenter. So those are not stereocenters. That leaves us with every one of the carbons that has not been dotted. And if we walk through each of those, we can just kind of confirm this. I haven't used orange yet. I really wish pink was one of the options. I like pink. This one is clearly attached to 4 different things. It's attached to a methyl group. It's clearly attached to a hydrogen, because nothing else is indicated, so we had to put the hydrogen in a 4th place. It's attached to whatever the hell this old mess is over here, and then it's attached to a CH2. Those are 4 different things. So this guy is definitely a stereocenter. Similarly, this guy's attached to 4 different things. This guy's attached to 4 different things. This guy is attached to 4 different things. This guy is not attached to 4 different things. It is attached to 2 methyl groups. And so, although they're not hydrogens, they might as well be. They are the same thing. The 2 methyl groups are interchangeable. You can't, it's not 4 different things. So we've got 4 stereocenters on this molecule. Now, it says assign RRS to each stereocenter. What I recommend you do, you can do this any way you like, first of all. If you have a system that works for you, sweet, good for you. If you don't have a system that works for you, you can find one. If you want my system that works for me, I would number each of the stereocenters you have identified, and then I would draw them. So here's carbon 1. All I'm going to draw is the bare stereocenter. I'm not going to draw anything on there. Instead of substitutes, I'm going to put numbers, and I'm going to put the numbers of importance. So if you've watched the lecture, you know that you rank things in terms of molecular weight of the atoms as you go down the chain. So what's nice there is this is actually a good example because it's complicated. The number 4, the lightest thing attached to it is the hydrogen. There's no question that hydrogen is the lightest thing because everything else is a carbon. All the other 3 atoms are carbons. So we're tied. So what we do there is we think, okay, so what's the next heaviest thing this carbon is attached to? The heaviest thing this carbon is attached to is another carbon. The heaviest thing this carbon is attached to is another carbon. Pick your carbon. The heaviest thing this carbon is attached to out here is a hydrogen. Hydrogen is lighter than carbon. We're good. Now, the next heaviest thing this carbon is attached to is a hydrogen. The next heaviest thing this carbon is attached to is another carbon. So we kind of rip apart those atoms. We see everything it's attached to. Then we move down to the next atom if we're still on a tie. So I think we have an example where there's still a tie after we do this. So what I'm doing here is I'm just writing a number. So stereocenter 1 has that arrangement of important things. Stereocenter 2, again, I'm just drawing in a stereocenter. Yeah, that's stereocenter 1. Try and, you know what, I'll use a laser pointer instead. Yes, let's try this. So now we're going to talk about stereocenter 2 here. And so it's just, we're going to, I don't think I can write if I'm doing that. No, okay. So it's attached to 4 things. 2 of them are in the plane. 1 is coming out of the plane. And 1 has to be going back. Now I've drawn 3 of them in the plane. That's just the way this is drawn. What this implies is any one of those 3 can be drawn going back from the plane. It's going to be the same molecule. I've arbitrarily decided to draw the 2-3 bond going back. But that was arbitrary. I could have picked either of the others. It would not change your answer. So it's not like, why did you pick that one? I just because. I knew that this one is coming out, so one of the other 3 has to be going back. It doesn't matter which one. Yeah, it just doesn't. It's all about perspective. So if we look at this and we try and think, okay, now there's no hydrogen attached, so this one's actually kind of tricky. So one thing we can do is we can look, okay, this carbon, and these 2 carbons are both CH2s. So they're carbon attached to another carbon and another carbon. But once we get, so we have that. This carbon here is got 2 carbons attached to it. So it's going to beat both of these because once we go to this one and we go to another carbon, but then we have to go to a hydrogen, whereas this one we go to a carbon and we go to another carbon. So this one is heavier. And number 3 is similar to number 1. We're attached to 3 different carbons. So what we have sort of is these 2 are lighter, these 2 are heavier. Now, what we have to do by the rules, if we look at them, these guys are going to be tied at these 2 centers, these 2 heavier centers. We're going to walk to carbon, carbon, hydrogen, carbon, carbon, hydrogen. So we're tied. So what do you do next? Well, your role is to go to the heaviest next chain. So for this guy, it's to go to this carbon. Right, you can't go backwards. This one's a CH3, so that's not good. So we're going to go to this one. And it's a carbon attached to a carbon. The next heaviest carbon attached to this one is obviously this one. It's a carbon attached to 4 carbons. So whereas when we look at this carbon, we think, what's the heaviest thing it's attached to? A carbon. What's the heaviest thing this is attached to? A carbon. That's a tie. What's the next heaviest thing this is attached to? It's a hydrogen. What's the next heaviest thing this thing's attached to? It's a carbon. So this is heavier than that. It took us a long way to get there, but we can assign it. And so that's my down. So that is number 1, and that is number 2. So if we look at these 2 carbons now, their next heaviest thing, they're both attached to is a carbon. We tied that in a hydrogen, so we move on to the next carbon. And the next carbon. And we have a double bond. How do I deal with the double bond? Well, the way you deal with the double bond is you pretend you break it and you kind of reflect it back on itself. So what we're going to practically do from this for a double bond is you kind of reflect back, so two of those. It's got this and it's got it again. And this guy's got it and it got it again. So we could go to this one. The heaviest thing this thing is attached to is a carbon. Sorry, I'm back in pen. I want laser pointer. The heaviest thing this thing's attached to is a carbon, then a carbon, then a hydrogen. This guy is attached to a carbon, and there was a hydrogen off of here too, because there was a hydrogen originally on this double bond. So that's all tied. This guy can now wander down to this carbon, where again we got these 4 carbons because that's going to be heaviest. This guy we're going to move down to this carbon, which again has 4 carbons. So that's going to be heaviest. Then, but this is where we differ, because this guy's going to run into the 2-methyl, sorry, it's going to be 2 methyl groups, methyl, shit, we're still tied. Then we have to go to the next heaviest one, which is going to be this guy. Next heaviest one from this guy is going to be this guy. And we still are on these, if we're comparing these 2 carbons now, sorry, so this guy we've walked all the way around to here, this guy we've walked all the way around to here, and we haven't broken his tie yet. So if we're on this guy, it's 3 carbons and a hydrogen. This guy is 3 carbons and a hydrogen. We're still tied. This can move down to here. This can move up to here. Here we're back at 4 carbons. No, this is where we started. We can't move back to here. So we started here. It needs to move to this CH2 now. And this guy's moved to this 4 carbon system. And we've broken the tie, because now walking this way has gotten us to a carbon with 4 carbons. Walking this way has gotten us to a carbon with a CH2. And so this is heavier than that. And this is a much harder question than anything you would face on an assignment. Once I actually saw how hard this one is, I really regretted that I put it onto something. It wasn't meant to go that long. So that this bolded line here, this one here, Alyssa? It's a CCH3, Amanda. Yeah, it means that's coming directly out of the page. So this carbon here makes 4 bonds to carbon. So these 4 here, these 3 here, they're kind of making a propeller, and then one that's coming straight out towards you. So what we're showing here is that there's kind of like a cycloheptane, and then there's kind of this bridging 5-membered ring that comes out of it. If you build a model of that, you can see that it's really hard to draw. This is the best way you can try and draw that. Luckily, that is by far, I think, the hardest of all the atoms to be looking at. So if we move on to, carbon 4. I'm just going to draw it like this, and this carbon here is that one there for carbon 4. And I've drawn it to be outside of the V because ideally that's how it should be. Because you shouldn't have it pointing inside sort of this little V you make there. The bond angle is funky. The reason it does that is we're trying to draw stuff in a plane that isn't really in a plane. And it's awkward, but it's because there's this 3-dimensionality and this branching and bridging and all this stuff that's going on. So if we're looking at this guy and we're trying to rank, well, the easy thing is hydrogen is obviously lighter than everything else. Similarly, this up one is the second lightest, this one here, because that's a CH2. Whereas the other two carbons that we're talking about here and here are not CH2s, that one is. So here we have a carbon attached to 4 carbons. Here we have a carbon that is essentially attached to 4 carbons. It's a tie. Next carbon. Each of these carbons is attached to 3 carbons because of that double bond tie. I'm not sure, maybe I'm lagging. I don't know. Hope I'm not lagging. It does actually seem to be lagging a bit. Yeah, sorry. I'll try and move a little, I'll try and watch my screen a little bit. So these 2 carbons, this one and that one, are both attached to 3 carbons and 1 hydrogen. That's a tie. We move to the next heaviest carbon. For this guy, it's going to be this guy. We never walk down these double bond paths, these fake paths. Those are, it's the rule is you don't. And if you look at the ABC of namings, it's all in there too, the book I provided. So if you look at this guy here, this is CH2. The heaviest carbon this is attached to is going to be this guy here, which is a carbon attached to 4 carbons. That's obviously going to beat out the CH2 because you're going to run out of carbons before you run out of carbons. This is ridiculously difficult to do, to try and do remotely. So we get 1, 2, 3, 4. Then we move on to carbon 3. Again, this molecule is a lot worse. You shouldn't need to. You're not going to need to go this far into tiebreakers on the test. This was a bad molecule, and I threw out the question. Again, on carbon 3, note that we don't have an up wedge anywhere. I've arbitrarily decided this one's going to be an up wedge. I could have chosen either of the other two, chosen this one as an up wedge. I could have chosen either this one or that one also as an up wedge. That would have been completely appropriate. But I just picked this one arbitrarily. Okay, so again, it's a little bit easy to assign number 4. It's the hydrogen. Hopefully at this point you can take a look and you go, okay, both. You can assign number 3 because it's the CH2, whereas these other two clearly have these stupid way too many carbons. No, I haven't mentioned. I will be mentioning. I'm driving up the tension, right? So I'll talk about it today. Then on this guy, we're going to walk this way and we're going to walk this way. So again, we have a carbon attached to 3 carbons and a hydrogen, carbon attached to 3 carbons and a hydrogen. It's a tie. But now we're stuck going to this guy, and this is a CH2, and that is not a CH2. This has got an extra carbon because of the dummy double bond. So this is heavier. So now we've done all this. We've assigned all of these. Yeah, chapter, yes. Okay, now we need to assign RNS to all these molecules. All these centers. So the hard part here is like, don't try and see why I'm trying to transplant, I'm trying to abstract it. So I just have numbers. I've done all that. I've separated that problem from trying to assign RNS. I just assign my numbers and then I can assign RNS. Okay, so when you're assigning RNS, if you remember, the only definition you need to remember is put the number 4 group pointing back and away from you. Put 4 back and away. If 1 to 2 to 3 is clockwise, R. If counterclockwise, S. That's it. So for this question, for example, there'll be a mark for doing this. And then once you laid this out properly, figuring out whether there are R and S. So in number 1, 4 is pointing towards me. You've got 2 options. Well, you got 3 options. You can move 4 away from you as many ways as you want. You can do that switching trick thing that we talked about last Friday, 2 Fridays ago. Or you can rotate it. Let's say we just rotate it. And all I need to do is rotate the stereocenter. I don't need to try and rotate the entire molecule. And if I just do a 180-degree flip, we'll mix it up. We'll do different things here, just for different learning styles. Or it's not so much learning styles, just different things are going to make sense to you. So all I've done is I flipped this thing like a pancake. You know, went from that to that. All my fronts became backs, all my lefts became rights. Now 4 is pointing back and away from me. 1, 2, 3 is counterclockwise, so 1 is S. Number 2 is the same issue. Number 4 is pointing towards me. Now here what I can do is I can do my switch rule thing. I can do 1 switches with 4. If I do that, 4 is pointing back, 1 is pointing out. 2 and 3 haven't moved. I note that I have done 1 switch. 1, 2, 3 is R, but I did 1 switch, so it must be the original one must be the opposite. So this one must be S. Because if after a switch it's R, before the switch it must have been S, because whenever you switch things, you always switch the stereo center. So I didn't rotate anything, I just, did my nano robot hands and swapped out 2 atoms. Number 3, conveniently 4 is already pointing back and away from us, so no need to do any work. We just do 1, 2, 3. It's counterclockwise. It is S. And then number 4 is pointing back and away from us already, which is great. Again, we don't need to do any work. It's clockwise. It's R. Then there is a single double bond. And we need to assign E and Z. So I'm just going to draw the double bond again. Real big like. Those are attached together. This is, I'm going to note that this is carbon stuff. Whenever you're assigning E and Z for a double bond, what you want to do is, first step, draw a line perpendicular to the double bond. This is line number 1. On both sides of line number 1, figure out which one is heavier. Carbon is clearly heavier than hydrogen. Whatever is attached to the carbon doesn't matter. Carbon is clearly heavier than hydrogen. Then you draw line number 2. Line number 2 bisects double bond. You need to figure out, are the ones on the same side or not? The ones are on the same side. So the ones are on the same side. So this is a Z. So I think there's 2 ways to remember E and Z. One is if the ones are on the same side, it's a Z, or if the ones are on the opposite sides, it's a E for opposite. It doesn't work as well. Bear with me. The second thing is This is organic chemistry. I think this is in my lectures too, because I just find this hilarious. This looks like an E. This looks like a Z, but since it's organic chemistry, it doesn't make any sense. So the one that looks like an E is a Z, and the one that looks like a Z is an E. If you have a different mnemonic for remembering this, go nuts. I like both of those. I also just like saying same side, so I go with that a lot. Oh shit. You're right. On the bottom one, it was a CH3, it was not an H. Doesn't change anything because this carbon does have more weight, because this carbon here is attached to, carbons and other carbons, and this carbon here is just stuck at a. Can we delete all this? Sorry, I started drawing too much shit and I confused myself. I'm really sorry. You're absolutely right. That is a CH3. It still wins because this is still a carbon with more stuff on it. That's the double bond I'm pulling from Melissa. You're absolutely right, Melissa. And that's where I need Sammer to jump in and tell me I'm off on my own track. Thanks, guys. Does that answer your question, Alyssa? Okay, I'm going to move on. Okay, so this question says draw and indicate. This is a good question. Draw and indicate the most stable and least stable, or draw and indicate the most and least stable Neuron projections of 3R, 3-bromo, 2,2-dimethylhexane, looking down the bonds between carbons 3 and 4. So this question, not a stupid naming question. This is the kind of level of naming you're going to have to do on a midterm or an exam. It's not complex. We're not asking for multiple groups. There's a main chain, there's a few substituents, and most importantly, there's some stereochemistry. There is going to be stereochemistry naming, but it's going to be simple like this, not stupid. I would never ask you to name that molecule we just looked at. So first thing to do is break down a name, make sure you draw the freaking molecule properly. It's a hexane. 1, 2, 3, 4, 5, 6. Make sure you have 6 atoms. It is a 3-bromo, so there's a bromine here. And it is a 2,2-dimethyl. So this is our molecule. And what you can actually do is sort of check off and go, okay, I've dealt with the hex, I've dealt with the 2,2-dimethyl, I've dealt with the 3-bromo. I now need to do this 3R thing. So what I'm going to do then is, I know there's a hydrogen here. So the trick is, when you're doing this, quickly assign priority. Hopefully that's not too difficult compared to what we just did. This is like a freaking cakewalk. The hydrogen's the lightest, the bromine's the heaviest. You've got 2 carbon chains. One of them's got a dimethyl group, the other one doesn't. So the way, if carbon 4, if the proton is backing away from me, this is an R, because I have 1, 2, 3. I want R, that's great. So what I'm going to do is I'm going to fill in the wedges. I got the bromine coming out from, and then the hydrogen going back and away. If I had drawn that circle and been an S, but I wanted R, I would have pointed a hydrogen directly towards me, because your hydrogen needs to be backing away from you, and you'd be switching 2 groups, and that's going to flip the stereocenter. Again, you can use any trick that works for you, but that will always work as well. Okay. Because if I switch the bromine and the hydrogen's places, right, I do 1 switch and it'll go to S. Now, I want to look down the bond between carbons 3 and 4. I've numbered priority on there, but if I'm numbering carbons, it's 1, 2, 3, 4, 5, 6. I've asked to look down carbons 3 and 4. You could do this backwards. That would be acceptable. You could look down 4 to 3 or 3 to 4. I didn't give directionality. I'm looking down 3 to 4. If I do that and I draw my Neuron projection, and I'm looking down that bond. The thing I am looking at behind the bond on carbon 4 is I'm going to see an ethyl group sticking down, and I'm going to see 2 hydrogens because there's nothing else on that carbon. Whereas on carbon 3, which is right ahead of me, I have essentially a terbutyl group coming into my face. I have a bromine in my right hand. I have a hydrogen in my left hand. It says indicate the most stable and least stable. So the most stable is going to be where I have the 2 biggest groups anti to each other. And that's what we've got here. The terbutyl is the biggest group. On the front carbon, the ethyl is the biggest group. On the back carbon, this is the most stable. The least stable Neuron projection I can draw is where the 2 biggest groups eclipse each other. So what I'm going to do is I'm going to freeze the back carbon. I'm not going to move the back carbon. You can freeze the front carbon if you like. I don't care. Both right. And then the front carbon is going to eclipse it. So everything on the front carbon is going to be directly on top of the back carbon. And where I'm going to try and mess you up here on this question is just make sure you rotate it right. So you want to keep going clockwise, counterclockwise, I guess, with the arrow drawn from terbutyl to hydrogen. And that's still the case here. Because if suddenly I switch the bromine into hydrogen, then I haven't made the same molecule. So that answers this question. Yes, you use A values if it's not clear. That's exactly what A values are for. The top group, if I look at this, 2 methyls and a methyl, it's really 3 methyls. Sarah. We were used to seeing the one in a chain, so we're not used to thinking of it that way, but that's a terbutyl group. It's just kind of hidden because one of them is in a chain. No, Hannah, it doesn't really matter. I try and draw more. Like you can always, obviously, we're looking at this slightly from the bottom right side with the view I gave. So it doesn't really matter if they're a little bit to the left or the right of the other carbon groups, as long as it's clear that they're more or less on top. I still give that full mark, even though I've clearly distorted these bond angles here, right? These aren't all the same. It's really problematic to do it because to get them all right, everything has to be on top of everything. It's really awkward. So I'm a little bit generous with eclipse confirmations like that. Yeah, you can use that one, Amanda. You can also pull up the Wikipedia A value table. There's one in textbook. No, I'm not sure there's one in textbook. Textbook's not the easiest thing to use. I hate virtual classes. Yeah. Okay, I'm going to skip this one. If we have time, we'll come back. So another set of questions I got is draw the following compounds using standard stick. So again, what we have here is a conversion of stereochemistry and naming from a word into a structure. And so again, what I'd really recommend you do, you can do this several ways. Keep track and make sure you have addressed every point in the name. So what I'm noticing here is this is telling me I have a double bond. This is telling me I have 2 stereocenters. This is telling me I have a chloro on 5, an iodo on 4, and a 2, you need to watch for it, ene. So there's a double bond on 2, and it's a hept. So my temptation, always with this, is to draw your main carbon chain first. 7 carbons. I'm arbitrarily going to call this carbon 1 and carbon 7. On carbon 2, I have a double bond. Now, before I go and figure out if this is right, I'm going to just put myself a little question mark here because it's double bond. I don't know if it's a Z or an E, and I have drawn one but not the other, but let's just draw on all the other substituents before I get too carried away. So on carbon 4, I have an iodine. On carbon 5, I have a chlorine. So check, 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 check. Now I need to deal with this. They said it's a Z double bond. That's a same double bond. That means my two heaviest groups should be on the same side of the double bond. And the way I've drawn it, they're not. They're on opposite sides. It's the two carbons are the heaviest things. So I need to redraw this. You know, if you want, you can even write Z on there. Okay. Carbon 4 needs to be S. So there's a hydrogen here. So let's take a look at carbon 4 and quickly assign priority. Hydrogen is number 4, iodine is number 1. Then there's two carbons. They're tied. This carbon is attached to a chlorine. This carbon is not attached to a chlorine. Chlorine is freaking heavy. If I go from 1 to 3, it's clockwise. That will be R, but it's not R, it's S. So the way I can get around that is pretend that the hydrogen is coming out towards me, because then it's going to be the opposite. So if the hydrogen is coming out towards me, and going from 1 to 3 gives me an R, gives me a clockwise. Sorry, 1 to 3 gives me a clockwise, and the hydrogen is coming out towards me. It's going to be the opposite when I flip the molecule around and point the hydrogen away from me. So it looks like an R, but the hydrogen is coming out towards me. It's just clockwise. And so it has to be an S. So that's right. And I can do the same thing for this carbon. Assign priorities. Chlorine is heavy. Hydrogen is light. Note that I'm drawing them on the outside of the V. If you draw them on the inside of the V, and by the V I mean, look, there's a V. If I draw them on the inside of the V, I'm going to get this wrong. I have to draw them on the outside, like this. Okay, so if I look at those, they're both carbons, but one of those carbons is attached to an iodine. The other carbon is not attached to an iodine. Iodine is even heavier than chlorine. So 2, 3. I go from 1 to 3, it's clockwise. I want it to be R. It is R if the hydrogen is going back and away from me, and the chlorine is coming out towards me. Now this is all a bit messy. This is my little sketching to myself, so I might redraw it. Because I want a nice neat drawing to hand in, and I don't want anyone to get confused about what I'm seeing. So that would be the full answer to this question. Did I lose anybody with that? Oh, I just didn't want to write CH3. Yeah, so just I gotta ask, can I go over the Z again? Why did I have to, oh, sorry, Sarah, why did I have to alter it? Because it was E, because I originally drew it like this. Whatever, there's stuff. And so when I rank the two heaviest groups, they're that. But if I look at where they are relative to that thing, the ones are on the opposite sides of the double bond. So drawing it that way, that trans double bond is an E double bond. But I didn't say E, I said Z. So that's wrong. So I can fix it really quickly. by making it the same. So now the ones are on the same side, so they're on the same side of the double bond. The two heaviest things on that on each of the carbons on the double bonds are on the same side. Okay. Does that work, Madison? And Sarah? Okay, so for Melitza's question, how did you include R, S, E, Z in a name? Do they all go in a bracket, and how are they ordered? This is correct. So what you do is they're all italicized. The E and Z go in front of the bracket if there are any, and they go E then Z because of alphabetical. And what you will normally do, though, is you'll normally put the number in front. And so normally the number takes precedence. So since there's only one double bond in here, I didn't need to say which double bond was Z. But I could have written this as, it would equally have been appropriate for me to write this as 2Z. Saying double bond on carbon 2 is Z. And then I'm just going to rank by numbers. So let's say I had a 2Z4E6Z. That's the way you do it. You do it in an increasing number. You do it in increasing number within the bracket for the S's and the R's as well. It's irrelevant over whether it's S or R, it's about which carbon it's on. So 1 goes first, 999 goes last. So the E and Z goes before the brackets. The R and S's go within the brackets. So it would not be wrong if we thought of Z and S, Z and E, I guess you mean, ISI, as trans and cis. Just think of the heaviest as a comparison point. Yes, it's Z is when the two heaviest groups are cis to each other, and E is when the two heaviest groups are opposite each other. So when the two heaviest groups are trans to each other. I'm careful not to say trans and cis double bonds because that only works if the double bond is only di-substituted. So it has hydrogens on both carbons and methyl groups. Because if you're saying a double bond is trans, it's a universal. Whereas a double bond with any more complexity, like the one we had back here, this double bond, it's neither trans nor cis. This methyl group is trans to this carbon, but this carbon is cis to that carbon, so is this double bond trans or cis? Doesn't make sense to use trans or cis. But the two heaviest groups are cis to each other, and so it's a Z. So you can still use the terms trans and cis, but you have to sort of define what you are transing and cissing relative to. So, answer your question, it's not wrong to think of Z and S, Z and E as trans, as cis and trans of the heaviest groups. That's fine, and that's accurate, and that's true. Just don't confuse Z and E for trans and cis, because they're not overall trans and cis double bonds. Often these bonds you couldn't assign them as one or the other. Well, Cl and I are not on a double bond. But that, so Alyssa is asking, so CH3 is less heavy than Cl, so we stagger with I. Yeah, but this isn't a double bond down here, down the middle. So there's no Z or E for this one. But let's say there was a double bond there. I just arbitrarily put one in. So if I had this, and I need to assign Z and E for this one. Then again, draw in line number 1, 1, 2, 1, 2, because iodine is heavier than carbon, chlorine is heavier than carbon, and then if I draw on line number 2, there's way too many numbers. Draw on line number B, because B is a number. The two ones are across from each other, so they're opposite to each other, so this would be an E double bond. But you couldn't tell me this bond is trans or cis. You can say it's a trans double bond or a cis double bond. That doesn't mean anything. You can tell me that's an E double bond. That's completely clear. You can tell me that the iodine and the chlorine are trans to each other. You could tell me that the iodine and the ethyl group are cis to each other, or that the chlorine and the propene group are cis to each other. Those are all true statements. But you can't say that double bond is trans or that double bond is cis. You can say that double bond is E. That is completely clear. But I think, Alyssa, it just wasn't a double bond, so I think we might be looking at this slightly differently. I'm not saying you're wrong, because I think you might be looking at a potential double bond there differently than me. Yes, we can, Sarah. Just send me an email with it. We're also not doing reaction. I can't remember what's on the reaction. Midterm 2. I think I posted all the midterms. So midterm 2 is probably for the second midterm, and we haven't done reactions yet, but we can definitely cover that. Okay, so the last question I want to cover today is going back to resonance. So I got this question. I'm sorry it's so small. I'll draw it bigger. It's just the text was really big and I didn't want to delete it. So what this question relied on is you realizing something funky is going on with the nitrogen down there. We don't normally draw in the lone pairs. We can, but if we do, that nitrogen's got no lone pairs. It is missing electrons. And there is something funky going on with it. Because that should be positively charged. This question is just fucked. I remember this question. It's just fucked. We're relying on nitrogen being the wrong thing. Like that just would have drawn that and saying that's neutral is just wrong. That nitrogen I should have had down there should have been doubly positive. I remember correcting this one. It's 2+. So let's say it's nitrogen 2+ down here. Now it's correct. Yeah, the assignments I've corrected have gone back, but when I post like corrections on Blackboard, on a Blackboard in front of the class, when a class is taking a midterm, those haven't made it into the revisions. Well, the reason we can figure out this is 2+ is let's say it has no lone pair. So Alyssa said, can we talk about formal charges for this? So let's just say we had this starting thing that we have got there, and we ignore the positive charge for a second. I just say there are no lone pairs on this, which is what I'm indicating. Nitrogen is valence 5. 5 minus 1/2 of the electrons in bonds. There are 6 electrons in bonds. There are 0 electrons in lone pairs. 5 minus 3, that equals 2. So it's +2. So nitrogen should have been 2+. So this is quite clearly an absolutely insane molecule. If we're trying to rank the resonance structures of this absolutely insane molecule, the one that is the best is this guy here. Why? Every atom has its full octet. Nitrogen, carbon, oxygen, everybody's got their full octet. Both of these things, you have an atom without its full octet. In one case it's carbon, in one case it's nitrogen. But worse than that, so first of all, if you have 2 atoms both without their full octet, and this is what I was really trying to evaluate with this question, and I just did not write 2+ because I'm an idiot. then what you're looking for is carbon stabilize the positive charge better if everybody's missing its full octet. This carbon's only got 6 electrons. This nitrogen's only got 6 electrons. They're both short 2 electrons. Better to have that on carbon. It's also a whole lot better not to have a 2+ charge on the same atom. That is just the worst. Because we're already talking about, hey, you want to delocalize charge. Now we've got 2+ stuck on one atom. Like that's awful. That number 3 one is actually so bad that although it was the starting point for the question, I wouldn't blame you if you didn't include it in the resonance hybrid. But let's say we do include it in the resonance hybrid. There's our 6-membered ring. There's a hydrogen. There's an oxygen. There's a hydrogen. There's our bond. The overall charge on this thing is 2+. The biggest delta plus is going to be on, well, the biggest delta plus is going to be on nitrogen. There's a delta plus on the oxygen, on the nitrogen, no matter what you do. So that would be what that would look like. Is there another one where there's a lone pair on nitrogen? Yeah, there is. And you can draw that. So let's draw it from here. You can absolutely do that. Now, this one here is not as good as this guy here, because although, you know, the carbons are more or less equal, we now have a positive charge on oxygen versus a positive charge on nitrogen. It's better to have it on nitrogen than an oxygen. Still a whole lot better than number 3. So I'd accept partial positive charge on that carbon as well. Everybody's got a positive charge. Because that's what happens when you're 2+. There's lots of positive charges to go around. So Alyssa said, isn't it bad to have a positive charge on oxygen? Wouldn't you rather it be on carbon? Which is a great question. I'm really glad you asked, Alyssa. Let's take a look at 2 different types of positive charge. Give me a second. I'm trying to think of how to draw the other one. Okay. So let's draw some resonance structures for both of these. Okay. Now, let's start just looking at this left-hand one here. Which of these 2 resonance structures, the top or the bottom, is the more stable resonance structure, the bigger contributor to the resonance hybrid? Okay, I say it says the top one. Any other opinions? So generally, the majority carries it, but I'm going to disagree with the majority here, and I'm going to go with Leon and Jeanette. And Dea, the bottom one has a full octet. The top one does not have a full octet. The carbon does not have a full octet. This carbon does not have a lone pair. It's got 6 electrons. Whereas down here, carbon's got 8 electrons, oxygen's got 8 electrons. The oxygen is formally positive. Definitely count out the formal charge. It's definitely +1, but there are 8 electrons around at oxygen, right? There are 6 in the bonds in a lone pair. It's carrying a formal positive charge. Yeah, of course it is. But every atom in that bottom one has a full octet. Whereas the top one, the carbon, does not have a full octet. And the most important thing to determine the stability of an atom, of a charge, is does everything have its full octet? Number 1. So this oxygen is formally positive. But it's not actually electron deficient. It's got, well, it's electron density deficient, but the electron count isn't deficient. Now let's look at the guy on the right. Which one of these two is more stable? Left or right? Madison, I love that you're thinking in like words in text. The oh shoot bottom. Like, oh damn it. Okay, Melitza's in on the left. She's saying the left is more stable than the right. Any other opinions? I love that you're opinionated. Okay, you're all coming down on the left, so my trick is going to fail. Yeah, you're all right. It's left. Because if we look at this, in both cases, the carbon and the oxygen are not full octets. The oxygen only has 6 electrons here. The carbon only has 6 electrons here. They're both kind of sucky. But carbon prefer, if this is now equal, these are both really positive atoms. And now an O+ under these conditions, an electron deficient O+ sucks. It can't stabilize that charge. It hates it. Carbocation is not that bad. But carbon with 6 electrons, no, it's not the end of the world. An oxygen with 6 electrons doesn't really exist. It's massively unstable. So when we went back to that question here, where somebody was saying, but isn't it better when the carbon has a positive charge than oxygen? Yeah, if they're both the same. If they both carbon can never have a positive charge and have its full octet. There's no way to make that happen. But if both the oxygen and the carbon have 6 electrons, C+ is better. But in this case, the oxygen has 8 electrons. It's got its lone pair. And so it's better. So keep an eye on those octets. It's important to keep an eye on the octets. I think Olivia is right that they both suck, but she'd say left, and that's exactly it. Which is, I think, what we just went over. Okay. That was fun. So midterm. The midterm covers up to last Friday's class. So what does that cover? Well, it covers all of the stuff we did on Lewis acids and intermolecular forces, and I think it's up to lecture 12 or whatever it is. All the stuff on conformation, all the stuff like on rings and rings flipping and rings doing all other sorts of other things. And then it also covers, are these things enantiomers or diastereomers? What does it not cover? It does not cover naming enantiomers. We didn't get to that till today. You do not need to name enantiomers. You might want to say, yeah, these are definitely enantiomers, and that might be part of your process. Go nuts. I am not going to ask you to convert a name into a structure or a structure into a name. I am not going to ask you to name a molecule. I will be doing that on the final because it will be with reference to R and S, Z, and E, but I can promise that it will be on the same order of difficulty as something like this. It won't be any harder than that. It won't be some stupid long name with lots of multiple chains and trying to screw you up. Oh, Samra, that is a very smart point. You know, you guys have a champion for the students there. It's good. No, you're right, Samra. I'll mark where the midterm's covering, what sections it covers, and I'll actually re-update the syllabus, basically saying every video above this counts. What's the format? It's going to be long answer questions. It's going to be on the format of the midterms that I posted. The way the midterm's going to work is Samra and I, and maybe another GA or two that I rope in, are going to generate, 10 versions, 5 versions, whatever, some number of versions of every question. We're going to put them into a Blackboard pool. It's going to pull one question of that pool from that pool for you. That question will be a long answer question. You will be able to go back on the midterm. So if you see a question you don't like, you can skip ahead. I'm going to make it so it shows all your questions at once, if I can. So you can also print it out. What you're going to do then is you're going to have the question posted in front of you. You can grab a piece of paper or a tablet or whatever, and you can write your answer. Once you have written your answer, you're going to take a picture of your answer. You are going to take that picture and you're going to upload it to Blackboard for the question. There's going to be a spot to upload your answer. And so we'll have your answer uploaded on Blackboard. I'm going to put in a practice uploading thing so you can practice uploading files. We'll probably accept JPEGs, TIFFs, bitmaps, PDFs, PowerPoints, Words, whatever format you want. Just none of these Apple proprietary ones that nothing else can open. But your cell phone probably takes the picture with the JPEG, and that's probably the easiest way to do it. So you get your cell phone photos and you upload your cell phone photos. It's probably going to be very slightly shorter than the ones I posted because the point is that it's going to be, those are 3-hour midterms. You're going to have 4 hours to do a 3-hour midterm. But my goal is that you kind of it's meant to be kind of a bit of a flexible time. So if you need to start a little early or start a little late, that's fine. So you kind of have a 4-hour window. The exam opens at noon, it closes at 4. Whatever's not uploaded by 4, tough shit. So I'm kind of building in sort of extra time in there for you to upload your questions. If you have accommodations, you will be given accommodations on a case-by-case basis. If you label the questions, can we upload one PDF with all of them? No, I'm sorry, you can't. The reason why is because we can organize the marking a whole lot easier. I know you want to do that. My GAs will murder me. And this just sucks. I'm sorry. It's not going to be a humongous number of photos that you're going to have to handle, but it's probably still more. You have 4 hours to write. I'm giving you a 3-hour midterm with 4 hours to do it in. That's why you're getting sort of that extra time, because you're getting 4 hours to do a 3-hour midterm, but I'm probably going to write it kind of like about 2.5. I think most of the midterms I posted I think they ended up being about 3 hours, so it's probably going to be something a little bit, it's going to be that length or a little shorter. We will not I don't know what Sarah means by that. The questions will not need the fixings that I did here because I can't make announcements and correct questions. So we're going to go through all the questions with a fine-tooth comb to make sure there are no errors in the questions. I managed it last year. the midterm had no errors in it, and the final had no errors in it, and I'm hoping I manage it again this year. Again, yeah, each question is going to be submitted as a picture separately. Any other questions? It is an open book exam. Yes, the best way to study is doing my assignments and take it, because if you look at the midterms that I posted, you're going like, those questions are kind of like the assignment questions, except easier. So doing the assignments is a really good way to study, because that's how my brain works. And I normally throw really nasty questions on the assignments with tricks in them. And so if you start getting used to seeing that kind of stuff, there aren't really, I'm not trying to trick you on the midterm. I am trying to trick you on the assignments. We do not stop for review. We just move forward. The content moves forward. If there are specific questions, I'm happy to answer them just like this. But I think next class, we're looking at the schedule is tough. There's just no space for anything. I think we're moving into the next thing. Oh no, we're still in stereochemistry next class, so we do more stereochemistry examples. But you know, I'm kind of open to answering questions. It's exactly what we're going to do in Melissa. Okay, have a really good rest of your day, everybody, and happy studying. Anything you didn't get done on reading week. Hopefully you're all refreshed. It's been a hell of a year. Yes, Melissa, that is fair. Yeah, okay, yes, we'll do some more of those questions, absolutely. Jeanette, I am going to say do what you like. I think both of those make sense. I think do as many questions as possible. If you understand, like, the best way to be prepared for this exam is to understand all the concepts and being able to apply everything. So I think it's a really good way to do all those assignments, because what the assignments are meant to do is you doing it and then go, oh, I got it wrong. Oh, maybe I don't understand this as well as I thought I did. I better go understand it. Like, they're meant to kind of act as speed bumps to you to make you think, I might not have this as much as I think I do. Because it's so easy to read the textbook and go, yeah, I get it. Or to look through the answer keys and go, yeah, this is boring. Of course I get this. Doing the assignments when you catch yourself and realize you don't quite know everything. Yes, submission is going to be multiple files. What if it was E and not Z? This question right here, Mohammed? Or did the other one kind of hang out there from your chat? You never hit enter, and that was like from an hour ago. How many questions can you expect? I don't know. 3 hours worth? Probably on the order of like 12 to 15. Okay, thanks everybody. Have a good day. I'm going to end my recording.